Welcome back to ME 760 Engineering Analysis 1. So this is the last lecture for this course. We will conclude with the linear operator, the Hermitian operators, and we will discuss the Strom-Liouville theory. I advise you guys to compile your notes that you already took during this class by the hands-out online. They are very valuable hands-out, so just print those and then stick them to your class notes. This will complete a very good reference for you in future if you want to return it back and look for anything. So most of the study notes or hands-out online are written by Professor Ken Schultz here at our Mechanical and Nuclear Engineering Department, because he has been teaching this course for several years, and he prepared those hands-out, and I'm using those for the first time for me teaching this class. So last time when we discussed the linear operators, and we stated that for a Hermitian operator we found 4 properties. The first one is the eigenvalues, like the Hermitian matrix. The eigenvalues are real. The eigenfunctions also are real, like the eigenvectors for the Hermitian matrix. So the eigenfunctions are real. The eigenfunctions are orthogonal. And finally, the eigenfunctions complete. They will form a complete set, so that you can, in principle, expand any function f capital of X as a function of the eigenfunction an multiplied by phi n of x, where phi n of x are the eigenfunctions. So it's exactly the same like the eigenvectors in the linear vector spaces, where you can write any vector in terms of the eigenvectors of your problem. To take an example, we started this example last lecture, and this is the Fourier series. So if you remember the last lecture, we wrote the differential equation as d2y by dx squared plus lambda square y equal to 0, and our linear operator here would be just O, or O is just d2 by dx squared, the weighting function 1, and we stated that our boundary conditions are just y at negative pi equal to y at pi, and y prime at negative pi equal to y prime at pi. Those were the 2 boundary conditions, and we found last time that our solution yn of x was given by the eigenfunctions, and those were cosine lambda n x and sine lambda n x, where lambda n will be 0, 1, 2, and here 1, 2, 3, and so on. You cannot start from 0 here because sine 0 is just 0. So those were the eigenfunctions, and since those eigenfunctions are complete set. So any function can be represented as f of x. Any function, for example, f of x, can be written as a naught over 2 plus summation from n equal 1 to infinity for an cosine nx plus summation for n equal 1 again to infinity bn sine nx. So we started here the summation for the cosine from 1, and we get out the first term when n equal to 0 as a naught over 2. And this will be valid from a to b, and a is negative by to by is valid from negative a to b, where from the orthogonality property we can deduce the value for an and bn, and this is just 1 over half the period, and this is the period here from negative pi to pi is 2 pi, so 1 over half the period, and you integrate from negative pi to pi multiplied by f of x cosine nx dx, and bn will be exactly the same, similar, and this will be from negative pi to pi f of x integrated multiplied by sine x integrated over dx. So if you want to generalize for any period instead of just pi to pi, negative pi to pi, so we will have the generalization for this where x is greater than a and less than b. This will be just f of x equal to a naught over 2 again plus summation from n equal 1 to infinity an cosine nx plus summation from n equal 1 to infinity bn sine nx. But we will remove the nx here, and we will put 2 pi nx over L and 2 pi NL over L multiplied by x, where now L is just A minus B, which is the width of the interval. So if A equal to pi and B equal to negative pi, this will give you what? 2 pi. So this will give you 2 pi over 2 pi multiplied by nx and 2 pi over 2 pi multiplied by nx. So you will return back to the same case over there. nx an cosine nx plus bn sine nx. Okay, guys? And again, the same formulas. You will divide by 2 divided by the period. So this is the half the period between A and B. Let's assume that AB is period. So this is half the period. So L, if L is 2 pi, and here is 2, so they will cancel out, and you will end up with pi here, and this is a to b, same, f of x cosine 2 pi n divided by L multiplied by x dx, and Bn will be equal to over L multiplied by a to b f of x sine 2 pi n over L multiplied by dx dx, where n for this case will be just 0, 1, 2, blah blah blah, and n for this case will start from 1, 2, 3, and so on. So this is just the generalization of the Fourier series expansion in any period or any interval a to b. So now let's study a very important theorem. It's called Strum-Liouville equation. So this equation, or the theory, said that most second order homogeneous ordinary differential equation can be written as operator L operated over y of x equal to d by dx multiplied by p of x dy by dx. Of course, y is a function of x, plus q of x y of x equal to 0. So this is not the same form that we used to have for the second order differential equation, yes? So if you want to transform it, this will be what? b of x multiplied by d2y by the x squared plus dp by dx dy by dx plus q of x y of x equal to 0. And now this is r of x. So this is the general form of a second order differential equation. Yes? So p of x multiplied by, this is general form. This is the general form of linear ODE with variable coefficient. This is the general form of the ODE with variable coefficient. So how we prove that this is true? So the generalized second order ODE can be written as d operated over u is just equal to some function f of x d2u y by dx squared plus some function g of x dy by dx plus some function h of x y equal to 0. This is the general form for a second order differential equation. So if we multiply D, the operator D or the operator equation D, by an integrating factor. This integrating factor is f of x equal to 1 over the function f of x multiplied by exponential of g of x divided by h of x dx. So you can call it t or x or z or whatever. Does not change anything. So when you multiply this equation by this integrating factor, you will have f d operated over y is equal to, you will notice that when we multiply this term by this integrating factor, f of x will cancel with f of x, and you will have the exponential function multiplied by d2u y by the x squared, plus we have the second term is g of x divided by f of x, so this will be g divided by f multiplied by the same exponential function multiplied by dy by dx, plus the last term will be h over f multiplied by y multiplied by the exponential of the same function here. So we can rewrite this equation as d by dx for the exponential function multiplied by dy by dx plus h of x divided by f of x multiplied by the exponential function again multiplied by y of x. So we can call this as q of x, and we can call this the exponential for this function d of x, and this will give us this d by dx for p of x, dy by dx equal to q of x multiplied by y of x. So this is the proof for the theory here that you can write any ordinary second order ordinary differential equation as an operator here has the form d by dx operated over p of x dy by dx plus q of x y of x. And the eigenfunction or eigenvalue problem associated with this or corresponding to this equation, let's call this equation star. So corresponding to star would be just L operated over y plus lambda omega of x multiplied by y of x equal to 0. We call this double stars. So we note here that all b of x, q of x, and omega of x all are real functions. So why is this important? Mike, if you can get the overhead projector, please. Okay, can you zoom a little bit? Okay, so we will see in the handout online that this is the general form for the eigenvalue problem for the Strom-Liouville theory. And you can write any second order differential equation, you can write it as in this form, eigenvalue in this form, with the operator defined by the Strom-Liouville operator. So you will notice that in the handout, we can write pretty much all the second order differential equations in terms of this operator here, with the appropriate substitution of the function f of x, b of x, q of x, and lambda and omega. F of x is just what? The integrating function. So you will notice that the harmonic oscillator is what? Y double prime plus lambda square y equal to 0. So you will notice that p of x will be what? 1. So this will give you y double prime plus q of x is equal to what? Q of x is equal to 0, so we do not have q of this term here. And lambda is equal to what? Nu square, and omega is equal to 1. So this would be nu square multiplied by y. So you will end up with y double prime plus nu square y equal to 0, and this will give you what? The harmonic oscillator equation. So if you look at the Legendre equation, you will notice that the integrating factor is 1. P of x is just what? 1 minus x squared. Q of x is 0. Lambda is what? L multiplied by L plus 1. And omega is what? Is 1. All the Bessel function, associated Legendre, Chebyshev one, Chebyshev's second one, the Laguerre, associated Laguerre, Hermitian, or Hermite polynomial, Jacobi, Matthew, Hyper, geometric, all the second order differential equation that we have been looking at during this chapter can be written in terms of only one operator, which is the Strom-Liouville operator. So we will look at the properties of this operator. If this operator is self-adjoint, what was the property of self-adjoint operator? Linear eigenvalues, linear eigenfunctions. The eigenfunctions are orthogonal, and the eigenfunctions form a complete set. So in principle, you can use those eigenfunctions to expand your solution in terms of those eigenfunctions, and then you will use the orthogonality to calculate what? To calculate the coefficients. Yes. So for the Fourier series, we use the boundary condition to get the what? To be able to calculate the eigenvalues and eigenfunctions. And the boundary condition was what? Y at pi equal to y at negative pi, y prime at pi equal to y prime at negative pi. So we have to define what are the boundary conditions for the Strom-Liouville operator, so that this will make the operator a self-adjoint. And if this boundary condition will make the operator self-adjoint, now the eigenfunctions and the eigenvalues will have the real values, orthogonal, complete set, and we can expand any of those ordinary differential equation using those eigenfunctions. Did you understand what's the important now of the Strom-Liouville theory? So it's a very elegant way of solving any second order differential equation with variable coefficient. Just you will know one operator, you will see if this operator is self-adjoint or not, and you will get the expansion for the eigenfunctions. Solution will be just the expansion using those eigenfunctions. So let's look for the the boundary condition for L that needed to make L as a self-adjoint. So boundary conditions needed for L to be Hermitian. Self-adjoint. So we will assume two real functions. F and G that they are L2 integrable. Can somebody remind me what's L2 integrable? That if you integrate the function, yes, over what? Over, you integrate those functions, the f star multiplied by f, yes, over dx, this will give you a number less than infinity. And we stated last time that a constant, for example, from 0 to infinity is not L2 integrable function. Yes, because it will give you infinity. So we will assume that those are those function fg. Then we will find the L dagger here, which is the adjoint operator for L. The adjoint operator for L is just G and L operated over F. Last time, if you remember, this was what? G and O operated over F. Yes? This was the definition for the adjoint. Yes? And we stated that this should be what? O operated what? G dagger and F. This was the definition for the adjoint operator. Yes? Now, the operator now, instead of O, the operator is what? Is L operated over F, and this will give us A to B G star of X multiplied by L operated over F dx. But we knew that J and F are real, G and F are real, so the complex conjugate of G will be the same function G, yes, multiplied by L operated over F dx. Again, we will do the same like last time, and we will do the integration by parts. So this will give us the integration from A to B. Before we do the integration by parts, let's write L. So what's L? D by dx multiplied by what? P multiplied by d by dx plus what? Q of x. Yes? There's no y. It's L. If L operated over y, you have to put here y, and you have to put here y. I'm talking about operator now. I'm not talking about the function, the differential equation. This is the definition for the operator L. Yes, guys? So now remove the L from here and substitute with this L. This will give you what? G multiplied by what? Multiplied by P df by dx or we can call this what? F prime all prime plus from A to B G multiplied by Q multiplied by F dx. Do you have any questions so far? You knew what I did. What I did here is the operator L is just what? It's just the derivative of P multiplied by D by dx for F. Yes? D by dx for F is what? F prime. And D by dx for this bracket is the prime here. And this is what I put here. Okay, guys? Plus G is G. And then the second term was what? Q multiplied by F. Okay, guys? So we will do integration by parts for this. And this will give us G multiplied by BF from A to B minus from A to B G prime multiplied by B F prime dx plus this is the two term for integration by parts for this integral here. Second integral will be the same, A to B GBF dot dx. Again, we do not want to have this in this format, so we have to do again integration by part again. So the integration by part again will give us GB F prime. This is will go down here minus, and this is G prime multiplied by BF from A to B minus is plus multiplied by BG prime all prime multiplied by F dx plus GP F dx.
That last term has a Q in it.
C to B. It's not B, it's a Q, thank you. So GQ, it's not B. Thank you. It's Q here. But when I wrote it P. Thank you. So what's this? It's the function G, the function P, the function F evaluated at the borders. Yes, at A and B. So if A and B, if this is a surface, so this is surface what? Surface term. We call it surface term. This is just the first part here. Yes? What you see here is the first part. So all of this must equal to the second part. Yes? And what's this must equal? This must equal to L adjoint operated over G and dot product, inner product was F, and this is what? A to B multiplied by P. Again, you will get what? The same operator. So the same operator will be just P multiplied by G prime all prime multiplied by F dx plus A to B GQ F dot dx. So if you look at this, and if you look at this, this is both those terms are what? Are equal. So for L to be self-adjoint, this should be equal to this. What's the extra term that we have it here? The surface what? Surface term should be equal to what? 0. So surface term should equal to 0, and this is the boundary condition. So your boundary condition needed for the operator to be a self-adjoint or Hermitian operator is your surface term equal to what? 0. And this surface term is just G P F prime from A to B minus G prime P F from A to B should equal to 0. And it seems that this is a harsh boundary condition. Yes, you have G, P, F. Okay, so the solutions of your equation, Y, will be G and F. Second order differential equation has two components, yes? Those two components will be G and F, for example. And you knew what's P of X from the differential equation. So it is not very restrictive, and there is many possibilities to achieve this, many abilities. If we have our Y function is the function F and G, maybe you will have maybe you will have Y of A equal to Y of B equal to 0, and this entails F of A equal to F of B and G of A equal to G of B. So if you have your solution as Y equal to F and G, and F of A equal to F of B, the function F at the boundary A equal to the function F at the boundary B, and the function G at the boundary A equal to the function G at the boundary B, this will satisfy the boundary condition that will make our operator self-adjoint operator or Hermitian operator. So this is one of the boundary condition. Another boundary condition might be Y prime of A equal to Y prime of B equal to 0, and this is, you see those two boundary condition for what? For the Fourier series, but it was not equal to 0 for what? For the cosine term. It was not equal to 0, it was equal to 0 for what? For the sine term, for example. And you might also have it like P of A equal to P of B equal to 0. You might have it Y of A equal to Y prime of A and Y of B equal to Y prime of B, for example. So there is lots of cases where we can have this is fulfilled. And when this will be fulfilled, our Hermitian operator, which is the Strom Liouville operator here, we can represent any second order differential equation with variable coefficient as this Hermitian operator. Then we will find, using the boundary conditions that will allow us to satisfy the Hermitian operator condition. Using those, we will find the eigenfunctions, and we knew that the eigenfunctions form a complete set. Then we can expand our what? Our solution in this complete set of equations. So instead of just solving the differential equation like before, we can expand what? We can say that y of x equal to the summation, like the Frobenius method, for example. You expanded your equation y of x as a power series. You substitute back in the differential equation, get the coefficients, and then once you get the coefficient and the indicial equation, and you get the coefficients, you just substitute back in the power series, and you will get what's the form of the solution. Very easy. Yes? So this is exactly the same here. So why we will apply this? It is applied in some important problems. So I will just conclude with the important applications. Important applications for the Strom-Liouville theory. One is Fourier series. And also we have Fourier-Legendre. You can apply it in Fourier-Legendre. You can apply it in Fourier-Bessel. F is Fourier-Bessel, and so on. The special functions that we just stated last couple of lectures. You can use it to find the solution of the inhomogeneous equation. For example, inhomogeneous second order differential equation, and this is L of y, L applied over y equal to g of x, and again you will need some boundary conditions. So what we studied today is L applied over y or operated over y equal to 0, but we can also use it to solve the inhomogeneous equation with the known boundary conditions. We can use it to find the Green's functions. How many of you here heard about the Green functions before? Only one? Okay, so it's some functions. If, for example, if you want to get in nuclear engineering, for example, if you want to know what is the flux at a point X, for example, based on or because of a source represented or found at X prime. So it is the same. For example, if you want to know what's the heat flux at a certain position R in cylindrical geometry because of heat source at R prime, and so on. So those are called the Green functions. And again, you can use it to solve second order partial differential equation. Partial differential equations. So with this, I will conclude the chapter, and also I will conclude the course. I highly urge you guys to go back and read the hands-out. So I did not bring this in the exam. So it's not, does not mean that I did not bring it in the exam that you discard it, because you will use it as a graduate student. You will use it in your coursework. So it will be highly appreciated if you return back to the hands written by Professor Ken Schultz and read this very valuable hands-out. And also if you have any book in mathematical analysis or let's say advanced engineering mathematics, or even if you search Google for linear operator theory, you will find lots of good information. So this is a very useful technique to be used in your graduate courses, for example, or graduate research. Did you have any questions so far? Okay, have a wonderful holidays, and again, the exam for you guys will be next Monday. Stop by my office and I will give you the exam. You have to sign again the exam paper in front of me. For those students for the online cohort, just email me and I will email you back the Word document or the PDF for the exam, and please sign it and attach the exam paper on your solution back to me. Thank you so much and have a wonderful holidays.